Okay, so suppose you have a bunch of genies. Suppose there's an infinite number of pool balls, each number, 1, 2, 3, etc. So remember what we said last time. There's this game that they play. 1 over n minutes to midnight. Okay. Maybe that's the name of the game. 1 over n minutes to midnight. Okay. So in the first instance of the game, they at that point in time, they put in the ball numbered n. Right? Ball numbered n, and then at midnight, how many how many balls are in the bag? How many balls are in the bag?
Midnight's never reached.
Midnight's never reached. Why not?
Because it just keeps shooting smaller and smaller. It approaches 0, but it doesn't reach. Well, 0 approaches 12 o'clock, but it doesn't.
Midnight's never reached. So the clock somehow them moving around stops the whole universe from time from progressing. Because I think what you're saying is something like Zeno's paradox, right? You're saying that an infinite number of things can't happen, and so it's just never going to happen, right? Okay, can I walk to the door?
Yeah.
Okay, but an infinite number of things happen between here and there. Between if I walk to the door, I walk halfway to the door. I walk another halfway to the door. I walk another half the distance to the door. Another half distance to the door, right? And yet time doesn't stop in that infinite number of actions, right? So I don't think time stops. Okay, time doesn't stop. Time doesn't stop. So let me ask you this: what balls are in the bag at the end?
It would be an infinite number.
An infinite number. So maybe all the balls are in the bag, right? All the balls in the bag, and there's an infinite number of balls. There's more balls than any number that you can think of, right? No matter what number you think of, there's more balls than that, right? Okay. So game number 2, what they do is they put a ball in and they take it out immediately, right? So the same genie just puts it in and takes it out. Next genie comes along, puts it in and takes it out. Okay. What happens then? How many balls are in the bag at midnight? No balls, right? That makes sense, right? No balls in the bag. And then the last thing we ended up with was suppose they put in the ball numbered n. So the next game was they take out the same ball number n, right? But in the next, so they do that. They play that game. They find it's not that interesting, and then next thing they do is they take out ball numbered n minus 1. Okay, and this is where we stop. Right. So how many balls are in the bag at this point? And maybe the first person doesn't just puts the ball in. There's no balls. He can't take out ball 0. There's no ball 0. Okay. So the first genie puts in a ball. The second genie puts in a ball and takes out the previous, etc., etc. Okay. So how many balls are in the bag now? Oh yeah, that's right. So people were saying 1. Right. Was 1 the answer? Was 0 the answer? Some people said 2. Okay. So the way to think about this maybe is to say, if there is a ball in the bag, what's the number of that ball? What's the number of that ball? Is it ball number 1? Is it ball number 1? Could it be ball number 1? No. When was ball number 1 taken out? Ball number 1 was taken out at time half a minute to midnight, right? At time when n equals 2, ball number 1 is taken out, right? Okay, maybe you say, okay, it's not ball number 1, maybe it's ball number 1,000,000, right? Maybe it's ball number 1,000,000. But what would you say to that person? If somebody said, oh, I think ball number 1,000,000 is in there. Or if I said, I think ball number 2 is in there, what would you say to that person?
Oh, it was taken out at 1 over 3 minutes to midnight.
Right, so ball number 2 was taken out at a third of a minute. 20 seconds to midnight, right, et cetera, et cetera. And you see that no matter what number you say, that any ball that you say is in there was actually taken out at some point in time before midnight occurred, right? So the answer is actually 0. There's no balls in there. Okay. Let's see. Okay. So then they decide to do something else, which is at 1/n minutes to midnight, they put in the n more balls. Okay. So at 1 minute to midnight, the first genie puts in one ball. The second at 1/2 minute to midnight, the second genie puts in the next two balls, number 2 and number 3, etc., etc. The third genie puts in 4, 5, 6. The next one puts 7, 8, 9, 10, etc., etc. Okay. Okay. So and then as of course as you head towards midnight, the bag gets heavier and heavier. Right at midnight, there's again infinitely many balls in the bag. Okay. Okay. Now, what happens if they put in n more balls and remove the last? Okay, they remove the last one.
Wouldn't that be the same thing as the other one? Because the last one for the first one is this first one. For the second one is the first one, and the last one is like that.
So let's see. So first there's one ball in, and then the next person puts in 2, 3, and then removes the last. The next, right? This is the first genie number 1. Genie number 2 puts in two balls and removes the last.
Increasing the number.
Increasing the number.
Oh, okay. Missed that. Sorry.
Puts in 2, removes the last. The next one puts in 3, removes the last. Next one puts in, 4 and removes the last, and etc., etc. Right? Okay. So what happens at midnight? Colin?
There's
Still going to be infinitely many balls, infinitely many balls in there, right? Because the balls that are in there, you see, you're going to get the first 2, you're going to get the first 4, you're going to get the first 7, right, et cetera, et cetera. This set of the balls at the beginning, the number of balls in there is increasing, right? Right. Okay. 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 The last thing that happens. So now they put in n more balls and they remove the first one. Now they remove the first one instead of the last one. How many balls are in there at midnight?
Same.
Any guesses? So Stefano says, same thing, there's going to be infinitely many. Infinitely many? I'll let you think about it for a minute. They talk to each other, turn to somebody next to you and say, I think there are 5 answers.
So like the next genie, second genie to put in ball number 2 and then pick up ball number 1. There's a
Alright, so we're playing the game with genies and balls again.
3, 4, 5.
At 1/n, then it's midnight. They put in n balls and remove the first one. So at time 1, they put in 1 and remove the first one. So at time 2, they put in 2 more and remove the first one on that list. At time 3, they put in 3 more and remove the first one on that list. The first one, the lowest number of all. Right? Lowest. Right, they move the first ball in the list. Right, in the bag is this.
But okay, so like of the say like the third genie comes along, when he puts like 3 balls back in, and
Yeah.
you put in like 1 and then like the 2 at the end, or just more at the end, and 1 is never put back into the ball.
So I'm seeing it like this. They put in, at time 1, it's going to put in 1 ball, and I guess remove the first one on the list, so he's going to remove that same ball. At time 2, put in 2 balls, and then remove the first one on the list. Right? At time, so this time 1, time 2. At time 3, they put in. I'm sorry, the next 3. That's probably the trouble. You put in the next 3 balls.
Okay.
Put in the next 3 balls. So I should say. Put in the next. The next n balls. Okay. And then remove the first one on the list. Okay. And time 4, you put in the next 4 balls, right? So. And remove this one on the list.
We still have infinitely many.
Okay, so what's the guess? Infinitely many? Other guesses? Other guesses? Okay, so I'm going to ask the question again. Can you give me the number of a ball? Can you name a ball that's in the bag at midnight?
No.
There are no balls in the bag at midnight. Again. Right? In the previous one, it was almost the same thing, where you put in a ball, you put in 2 more balls and remove the last. Put in three more balls and remove the last.
Oh, yeah.
Put in 4 more balls and remove the last. And if you said, at that time we said it's pretty clear that there's infinite many balls in the bag, right? And if I said, what ball? Give me the name of a ball that's in the bag. You could say ball number 1. Right?
Oh.
Ball number 1 is in the bag. Ball number 2 is in the bag. Ball number 3 is in the bag. In fact, all the balls are in the bag, right? Okay. Now here, tell me the name of the ball that's in the bag. Tell me the number of a ball that's in the bag.
But like, it keeps growing more than it keeps losing because as n increases. you
Tell me the
still
number of a
lose
ball.
the same number.
Tell me the number of a ball.
I can't.
Okay. So as you see, right, ball number n is removed at time 1 over n plus 1 minutes to midnight. Right. Ball number 1 is removed at a half a minute. Ball number 2 is removed at a third of a minute to midnight. Ball number 3 is removed at a quarter minute to midnight, etc., etc. Okay. So anyway, so this is just to give you, to just show you that the notion of limit or infinity is a little bit tricky, and so one has to be careful with it. Okay. So the notion of limit. So this is not exactly the same thing, but it's very closely related. In some sense, it is exactly the same thing. So 2.1, the concept of the limit. Concept of the limit. So let me just ask you first. Does anybody know what the limit of f of x being L as x approaches C means? Does anybody know that? Stefan?
Limit of x as x approaches C is L.
Yes, what does that mean?
Oh, like the value of y, I guess, is approached as x approaches the number specified by C.
Okay, so as x tends towards C, f of x tends towards L. Right? I think that's a pretty common, intuitive idea, right? That's sort of your intuition of what a limit, what the limit means. Does it say one comment? Does it say anything about f of c? Is this a statement about f of c, f at c itself? No. Right? Doesn't say, does not say f of c equals L. Okay, and your picture is like this. Here is C, here is L, right? And you're saying that as your inputs, as your x's, as you take different x's, and your x's get close to C from either side, right? You take different x's and they get closer to C, then the outputs, right? The heights, f of x's, right? These f of x's get closer and closer to L, right? Right. So the graph of it will look, you have something like this, where the heights of these points get closer and closer to this point, to C, to this point C comma L. Okay. But we're not saying anything about what happens at C itself. The function could take on some other value. Okay. At the University of Chicago, I think I heard about a piece of graffiti, bathroom graffiti, at the University of Chicago. I think like this: the limit of fun as x approaches the University of Chicago is 0. Right? As you get closer and closer to the University of Chicago, fun approaches 0. Okay. Okay, but this actually displays some ignorance about the notion of limit, right? Because, this is just saying that as you get close to the University of Chicago, the fun tends to 0. It does not say anything about fun at the University of Chicago, right? Fun at the University of Chicago could be ignorant or something like that, right? Okay, so that's, the graphic graffiti displayed some level of ignorance. Okay. Okay. Okay, so we're just going to run through some of the examples that they give in the text. I think they're good examples. They sort of each illustrate a different facet of the notion of limit. Okay. So let me say that this is not the definition. Okay, this is not the definition of limit. This is rather just your sort of intuitive idea of what it is. This is not at all what we mean by limit. It is, but we're going to make it mathematically precise. Okay. So let's run through this set of examples. Example 1, we have some function f of t equals t squared, and you want to consider the limits of these functions. As t goes to 0. Okay. So what do you think? If f of t is t squared and t goes to 0, what's going to be the limit? Okay. Think for 5 seconds. Okay. What's the answer?
0.
Mariah? 0? Okay. 0. Anybody? I think everybody will agree that it's probably going to be 0. Right? Now, why do you think that?
I plugged in 0.
You plugged in 0. Okay, even though we just said that the value of the function at the point might not be the value of the limit as you approach that point.
Yeah.
You did it anyway. It happened to be right in this case. Okay. What if I have a function like this? T squared for t not equal to 0. Okay. Limit of g of t as t goes to 0. So this is a function. It looks like your old function, but it's not defined at 0. Okay. It's not defined at 0. What's the limit of this function as t goes to 0? Victor?
Well, the limit would still be 0 because all the other numbers are approaching 0. Just at that certain specific point, it is not defined.
Okay, so it looks to me that when you say all the numbers are approaching 0, you're thinking of the graph, right? Okay, so in your mind, you've got this graph. So you're saying, well, look, the t squared function is this parabola, right? And as you get closer, as the inputs, as the t's get closer to zero, the outputs also get closer to zero, right? Even if we eliminate this point here, still that's going to happen. As the t's get closer to zero, the outputs are going to get closer to zero. Okay. Okay. So that's good, right? You can see, so you can think of this thing, so visually or geometrically. Okay. So there's another way to think about this. Sorry. There's another way. Suppose you have no visual sense. Okay. Suppose you have no visual sense. Suppose, for example, you are unable. You're a one-dimensional person. Okay. You're from a one-dimensional world. You have no idea what this two-dimensional graph is. Okay. Or you're.
I like this.
Okay. Yeah. Yeah. This is you. Okay. What is this two-dimensional stuff? I have no idea what you're talking about. Okay, or I mean, this is not so unrealistic because we can certainly think of graphs in 4 dimensions, right? Which we as 3-dimensional features cannot visualize, right? So okay. Okay. And somebody says, well, what's the limit here? How, if you didn't have a sense of graphical sense, a visual sense, then how would you think about it? Here's one way. You'd say, let's see. Say, well, look, if I'm looking at the absolute value of t squared, right? So I'm looking at either of these things, right? T squared as t approaches 0. And I'm going to look at the size of the size of this. Okay, right. That's the same thing as the absolute value of t quantity squared. Right. That's the same thing as absolute value of t quantity squared. And you see that is smaller than the absolute value of t. Right. When for t less than 1. So you make an algebraic observation. Okay. By algebra, you just by numbers, you see that the absolute value of my output is smaller than the absolute value of my input. Okay. Is this clear here? That the absolute value of t squared is the same thing as absolute value of t quantity squared? Okay. Is that clear? How about this one? That absolute value of t quantity squared is smaller than the absolute value of t. Stefan?
I don't understand why you would go that direction. Like, how would you maybe go in that direction? Like, for what reason?
Hold on for a second. It'll be clear. Okay. Do you see why this is true? This is true because this thing here, absolute value of t squared, is the absolute value of t times the absolute value of t, right? And when t is smaller than 1, this is smaller than the absolute value of t times 1, right? So when you take a positive number that's smaller than, positive number that's smaller than 1 and you square it, it becomes even smaller than what you started off with, right? You know this, right? If you take a half and square it, it becomes a fourth. It becomes something smaller. Any number smaller than 1, you square it, it becomes smaller in size. Okay. So if somebody said to you, oh, what's the limit of f of t? What's the limit of t squared as t goes to 0? You'd say, well, as t is going to 0, if t is going to 0, and my outputs, the size of my output is smaller than that, so t squared is also going to go to 0. Okay. So then you'd say, observe. This is true, right? So as t goes to 0, the absolute value of t squared also goes to 0. Right? But just intuitively, right? As t goes to 0, this is going to go to 0, and t squared is something smaller than that, so that's also going to go to 0. Yeah, Claire.
Shouldn't it be t squared is less than, the absolute value of t squared is less than the absolute value of t for when the absolute value of t is between 0 and 1? Like, how would it work for negative numbers?
Oh, this is always, absolute values are always greater than 0. So you sort of leave that out. It's implicit. Yeah. But if you want, you can put it in. It's certainly true. Yeah. Okay. So even without a visual sense, algebra can give you a sense of what the limit is. Okay. You can have some sort of algebraic argument that tells you what the limit's going to be. Okay. Any questions about this? Okay. Example number 2. The limit of x squared minus 6x plus 6 over x as x tends to 5. Okay. So in the book, what they do is they start plugging in numbers. And they take numbers like 5.1, 5.01, 5.001, 5.0001, et cetera, and they look at the outputs, right? They look at the outputs, and what they see is that those numbers tend towards 1/5. Okay, so using numerical data. So they start plugging in some numbers, and they say, oh, it looks like this thing tends towards 1/5. Okay.
What do you mean by tens? What do you mean by tens?
The numbers get closer and closer to 0.2.
Oh.
Yeah.
I thought in the book they just plugged in 5.
Oh, is that right? Okay,
Yeah.
so maybe.
Okay. I think.
Okay. Let me. So maybe that's not what they did. But okay, but you could do it that way. I mean, you could that if you did that, the numbers would tend towards 1/5. Okay, so I guess what the book actually does is they just plug in 5, right, and they get 25 minus 30 plus 6 over 5, which is 1/5. Okay. Okay. Yes, Stefano.
When you were talking about the method that you just used,
Yeah.
you get closer and closer to
Yeah.
the number.
Yeah.
Since there's no specified like which direction you're approaching from, you
Mhm.
can go either greater than 5 or less than
That's
5.
right. That's right. So it would have to happen from both sides.
Okay.
Okay.
Yeah.
Okay. So, okay. So, and this turns out to be right. So if you just plugged it in, or if you took some numbers and started heading towards it, the limit actually is 1/5. So you have to be a little bit careful. So it turns out that so what's the point? For this function, the limit of f of x as x tends to 5 is actually f of 5. Right? You can just plug in the number. So sometimes it works, and yet sometimes we say it doesn't work. Okay. So for some functions, it's okay. The limit of f of x as x goes to c actually equals f of c, but not all. Okay. For some functions it works. So another comment, maybe numerical approximations can give some idea of the limit. Maybe. Sorry, what?
No, it's okay. Go on.
Numerical approximations. Sorry, what were you going to ask more?
I was going to say, so how do we know which functions that were?
Yeah, we'll get to that.
Okay.
Yeah, right now I'm just throwing out some things that will happen. Okay. numerical approximations maybe will give some idea of the limit. The thing is that you never know what's going to happen. If you never know what's going to happen. It may be that you take some values and it seems like they're tending towards some limit, but it turns out that as you get even closer, it tends to something else entirely. Right? So numerical approximations maybe can give you some sense, but they're not something you want to rely on. Okay. They're not something you really want to rely on, because you may go down to 5. It may be as intended towards 5.00001. The values were tending towards 1/5, but you didn't notice that if you zoomed in even farther, something else happened entirely. It tended towards 1 million or something. Yeah.
So if we were to graph this,
Yes.
wouldn't 0 not be included?
Wouldn't say again?
0 wouldn't be included, right? That would be included.
0 wouldn't be on the graph. I mean, there'd be no value of 0.
Okay.
Yeah, there's an asymptote at 0. Certainly. Yeah. Fortunately, we're tending towards 5. So we're asking about what happens at 5. Other questions? Okay, and that your question, Leah, actually is right along the next lines of the next example. The limit of x squared minus 4 over x plus 2 as x tends towards negative 2. So at negative 2, as you going to see, this function is not defined at negative 2. But what can you do? Who knows what you can do with this thing? Yeah.
You make the final drop x plus 2 into x minus 2 and then you cut out the x.
Okay. You say, well, look, I can factor the top. I can factor the numerator into x plus 2, x minus 2. Right? And which is, of course, just going to be x minus 2. Right? Excluding at x equals minus 2. Right? This, let me write it like this. X plus 2, x minus 2 over x plus 2 is just x minus 2 whenever x is not equal to negative 2. Right? At x equals negative 2, the left side is undefined. So it doesn't make sense to talk about this at x equals negative 2. But as long as you stay away from negative 2, then this is true.
How do we know it's undefined in x negative?
Well, because if you put in a negative 2, you're going to get this 0 on the bottom, right? And so it's not defined.
Cool. But after you cross them out, you can just plug it in.
So you can cross them out as long as they're not 0, right? You can't say if you have a 0 on the top and 0 on the bottom, you can't just you can't just cross out zeros, right? It's okay to cancel when you're multiplying by some non-zero number. It's not okay to cancel when you've got if these numbers are 0. Okay.
And you can't, I understand what you're saying, but you can't just cancel x plus 2 over x plus 2 and then just pretend like it's never even been there since you
right.
Since it's equal.
But when x is not equal to negative 2, then these things are not 0, and you can cancel them. Okay, that's the thing. When away from x equals negative 2, these are non-zero numbers, and you can cancel them. But at x equals negative 2, then this left thing becomes undefined. Okay. And so what's the limit going to be? What's the limit of this thing? Well, it's going to be negative 4.
And you found that because you could plug it in.
Yeah, this is one of those plugging in guys. Yeah.
But question.
Yes.
I thought we just said we can't plug in negative 2.
Yeah.
That was
Okay.
fine
let me say it this way. Okay. Okay, so let me see this. If we look at this function here, right? If we look at this function, then this function is just x minus 2. Okay, away from negative 2. Okay, so here's negative 2, and the function 2, 3, 4. Basically, what we're saying is that away from negative 2, the function looks like this line. I mean, the function is, so what's this function? This is the function right here. Right? The function is exactly x minus 2, except at this point where it's undefined. Okay. And maybe you can just say, by looking at the picture, as x tends towards negative 2, what we're going to get is negative 4.
Okay.
Okay.
Okay, that makes sense.
Okay.
And that's when it reaches.
That's what it tends towards. But at x equals negative 2, it actually has no value.
Okay.
Yeah.
So what's the difference between a limit and an asymptote?
An asymptote is a line. It's a related idea. It's a related idea. So one thing we'll talk about soon is something called a limit when the limit of the function is infinite as x approaches some point. Okay, and the picture for that is something like this, right? You have, as x approaches c, the function tends towards infinity. Okay, and that's what's called a vertical asymptote. Okay, so it's not, but this is not an asymptote, right? Infinite limits are related to asymptotes, and then finite limits are not asymptotes. But the notion is quite related. Good. Okay. So anyway, so this example is mainly to get across the idea that the limit, what's the point of this? The limit is not dependent on the value at c, but rather as x approaches c. Right. So x is approaching negative 2, but it's not equal to negative 2. Because it's not equal to negative 2, we can do the cancellation. And then we see that the value is negative 4. Sometimes as a teacher, you're teaching and you get in a panic. Like, how am I going to explain this? Maybe I can explain this. Maybe I can't explain this. And you sort of fall down this deep well of desperation. And then you're like, okay, no, I think I can explain it. Yeah. Okay. So the last two examples are the most important. So examples 5 and 6 are the most important. And the idea is this. Here's the right. If the limit, right, limit of f of x as x approaches c actually is L, we should be able to answer the question how close, right? So think the limit is L means that for x close to c, f of x is close to L, right? Or as x gets closer to C, f of x gets closer to L, we should be able to answer the question, how close must C be to x to ensure f of x is within 0.1 of L. Okay. If, as x gets closer to C, f of x gets closer and closer to L, well then, you should be able to answer this question, right? If somebody says, well then, I'd like your f of x to stay within 0.1 of L, how close must x be to C? Right? You should be able to answer that, right? If your function's limit actually is L at that point. Does that seem reasonable? Right? You're telling me that as x gets closer to C, f of x gets closer and closer and closer to L. Well, you should be able to answer this question then. How close must C be to x to ensure that f of x is within 0.1 of L? And you should be able to answer it if I say, how close must C be to x be to C to ensure that f of x is within 0.1 of L, right? Or for 0.001, right? In fact, for anything, you should be able to answer the question, right? If you're telling me that f of x gets arbitrarily close to L, you should be able to always answer this question. So in fact, this is the crucial notion, the crucial fact about limits. And this is what we're going to take as this is basically the idea of wire stress. This is the right way to talk about limits, to define limits. So it is the property we'll use as the definition. Next class. Okay. So let me give you a simple example. Okay. The limit of 2x as x approaches 3 is 6. I'm sure you believe that, right? As x approaches 3, 2x is going to tend towards 6. Right? Okay. So, so here's a picture, 1, 2, 3, 1, 2, 3, 4, 5, 6. Right? Here's the point. Go like this. Okay. And suppose somebody says, how close must x be to 3 to ensure 2x is within 1. Let's say 2x must be within 2 of 6. Okay? Who can answer this question? How close must x be to 3 to ensure that 2x is within 2 of 6? Alvin? Within 1, right? Certainly. Right? As long as we stay, here is 3, as long as we stay between 2 and 4, right, the outputs are going to stay between 4 and 8, right? They stay within 2, right? Here's 6 plus 2, here's 6 minus 2. As long as I stay within 3 minus 1 and 3 plus 1, then my outputs stay within 2 of there, right? Okay. I'm going to rewrite this. What delta x minus 3 must be less than what delta to ensure 2x minus 6 is less than 2. So I'm just rewriting it. Right? the distance, how close do we have to be to, how close must our x's have to be to 3 to ensure that this 2x is within 2 of 6? The distance from 2x to 6 is less than 2. Okay. Does everyone see that I've written exactly the same thing?
Much more complicated.
Just much more complicated. The distance of x is 3. Yeah. Right? How close? This is what delta? Right? What delta do you need? What delta do you need? Right? What radius do you need here? So that if you're within delta of 3, then this thing is within 2. This thing is within 2 of 6. Okay. Okay. Yeah.
Sorry, why'd you say 8 instead of like 4?
Sorry, this is a delta. This is a d.
Okay.
This is a d. Maybe I should call it an r for radius. Okay. This is a delta. People use this as for to. That's capital delta. This is lowercase delta. Sorry. Sorry. Okay. Hey, it's just the radius. This delta means the that little radius, the radius of your interval. Okay. 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 So now, what have I said? What delta ensure for what delta will x minus 3 less than delta ensure 2x minus 6 is less than 0.2 within 0.2. What delta, right? If I say, I'd like you to stay within 0.2 up here, yeah, I want you to stay between 5.98 and 6.02, well, how close do I have to be down here? If I'm going to be within 0.2, right? Here the delta being 1 would work. In the above one, delta being 1 worked. What about in the next one?
Question.
Yeah, that's different.
Yeah. Will the relationship between this, like the x value, the y distance, or like the x be different depending on what the equation is and what the
Yes.
function is?
Yes.
Okay.
Yes. So we're doing a very simple one.
Okay. Yeah.
Yeah. So how close do I have to be? Because I want to stay between 6 plus 0.2 and 6 minus 0.2. 0.1 will do, right? As long as I stay
Find
within.
that algebraically. Do you just like plug it in?
So does everyone see that 0.1 will do it for you? Right? As long as you stay within 2.99 and 3.01, then your outputs are going to stay there, right? If I said what if I said 0.002? What if I said 0.02? 0.01, right? What if I said within epsilon? And I don't tell you what it is, just some number epsilon. What do you think the delta will be? Epsilon over 2. Epsilon over 2 will do it. Delta being epsilon over 2 will do it. Okay, and let me show you how you can see that algebraically. Sorry to keep you over a minute or two. Right? You're asking what delta ensures x minus 3 less than delta implies 2x minus 6 is less than epsilon. Okay. And what you'd say is, well, here's your thinking. Think. 2x minus 6 is the same thing as 2 of x minus 3. Right? So if I want this to be less than epsilon, certainly if x minus 3 is less than delta, then if x minus 3 is less than epsilon over 2, then this thing is going to be less than epsilon. Okay? Okay. And so, I'll say it again, right? You're trying to find a delta so that this implies that, right? And you say, well, let's look at this thing. This thing is the same thing as that, right? 2x minus 6 is the same thing as 2 absolute value x minus 3, right? And I want that thing to be less than epsilon. Well, if x minus 3 is less than epsilon over 2, then 2 absolute value x minus 3 because they be less than 2 epsilon over 2, epsilon, right? So if this happens, then 2x minus 6 equals 2. This is smaller than 2 epsilon over 2. That's to say epsilon. So just take delta to be epsilon over 2. Okay, and that's basically what you're doing over here when we did the concrete list. When you said you wanted to be within 2 of each other, you figured out it was 1. When it was 0.2, you figured out it was 0.1. What you're doing secretly is actually this algebra. Okay, sorry to keep you over. That's it for today. It's hard thinking. I know it's very new stuff. Go home and think about it. This is the most complicated idea in the course, I would say.